Hello everyone. Today's lecture is on planar gamma camera, quality control, and the fundamentals of emission tomography. Let's look at the objectives for today. After today's lecture, students will be able to identify each component of a scintillation camera. Students will be able to explain the uses of different collimators. Students will also learn the fundamentals of an emission tomography system, and students will learn about some artifacts of an emission tomography system. In order to measure the rate of accumulation or the distribution of radionuclide activity in the body, a detector capable of detecting and measuring that activity is needed. Most detectors used for measuring radioactivity in the body are called scintillation cameras. Scintillation cameras are made from sodium iodide scintillation crystals. Here is a brief historical note. The first scintillation camera was assembled in 1956 at the University of California by Hal Anger. Its advantage over other devices at the time, like the rectilinear scanner, was its ability to collect static data over a large area of an organ simultaneously. This camera contained a 6 mm thick sodium iodide crystal of 10 cm diameter. It was coupled to 7 photomultiplier tubes, each 3.8 cm in diameter. 6 of the photomultiplier tubes were arranged hexagonally around a seventh tube placed at the center. The photomultiplier tubes were optically coupled to the scintillator by mineral oil. Modern tubes now have wider diameter crystals, more photomultiplier tubes, and better optical coupling with light guides. Let's look at some details of the single crystal scintillation camera. A single crystal scintillation camera can be broken down into 4 sections: the collimator, the detector, data processing unit, and the display unit. The detector consists of the single crystal, the photomultiplier tubes, the light guide, and the preamplifiers. The diagram of the detector head is shown with the various parts labeled. The collimator is placed close to the crystal as shown. We shall learn about the collimator next. There are multiple collimators used with nuclear medicine scintillation cameras. They are shown here as the parallel hole collimator, the pinhole collimator, the convergent collimator, and the divergent collimator. Apart from the pinhole collimator, the other collimators are made of small, straight cylinders separated by lead or tungsten septa. The pinhole collimator is made of a lead cone with a hole in the middle. Collimators allow gamma rays and X-rays coming from certain directions to reach the scintillator while blocking others. Collimators are made of high-density, high atomic number materials like lead. The parallel hole collimator is the most used collimator in nuclear medicine. It has thousands of parallel holes shaped as squares, hexagons, or round holes. The partitions between the holes is called septa and is made of photon-absorbing material. Collimators used for higher energy photons have thicker septa than those used for lower energy photons. The resolution of a parallel hole collimator approximately depends on the hole size, septal length, and the distance of object from the collimator, while sensitivity approximately depends directly on septal hole area and inversely on septal length. There is an inherent trade-off between having larger holes in the collimator, which means poorer resolution but higher sensitivity, and smaller holes, which means better resolution but lower sensitivity. Most scintillation cameras used in nuclear medicine come with a variety of collimators. Examples are low energy high resolution LEHR or low energy all-purpose LEAP. In parallel hole collimators, image size is not influenced by object to collimator distance, but spatial resolution decreases with object distance from collimator. Field of view also is unaffected by object distance from collimator. Another type of collimator is the pinhole collimator. It is used for magnification imaging of small objects like the thyroid or parathyroid. It consists of a lead or tungsten cone with a small hole in the middle. It works on the same principle as the pinhole camera. Magnification depends on the object distance from the pinhole, so an object can be magnified or minified. The converging hole collimator is one that has holes shaped to appear to converge to a focal point in front of the camera. Converging hole collimators produce a magnified image of objects. The magnification increases as the object distance from the collimator increases. A disadvantage is the decrease in field of view as the object is moved farther from the collimator. Converging collimators are rarely used in nuclear medicine because of the varying field of view and magnification with distance. The diverging hole collimator is one that has holes shaped to appear to diverge from a focal point behind the camera. A diverging collimator produces minified images of objects. The minification increases as the object distance from the collimator increases. An advantage of a diverging collimator is a large field of view for imaging large anatomies. Diverging hole collimators are rarely used in nuclear medicine because of poorer image quality compared to parallel hole collimators. A collimator may be high resolution, meaning it has multiple tall cylinders of small diameter separated by septa. This type of collimator blocks photons from reaching the detector because of having numerous cylinders and septa and is therefore also low sensitivity. The opposite of that is a collimator having fewer short cylinders of wider diameter and thinner septa. This type of collimator is low resolution but also higher sensitivity because it blocks fewer gamma rays from reaching the crystal detector. This table shows some performance characteristics of commercial parallel hole collimators. The best resolution is the low energy, high resolution camera LEHR, and the best sensitivity is the low energy, high sensitivity LEHS camera. This table summarizes the effect of increasing object to collimator distance on collimator performance for parallel hole collimators, converging, diverging, and pinhole collimators. Let's look next at quality control. Quality control is important to keep imaging equipment performing at a high level and to discover performance issues before they affect image quality. Quality control tests performed for gamma cameras include peaking, uniformity, spatial resolution and linearity, and also efficiency. We shall start with peaking on the next slide. Peaking is done to center the energy discrimination window on the photopeak of the energy of the radionuclide. This is an image of the energy spectrum with the photopeak shown. The vertical lines are energy window limits. Peaking can be done before each day of use by using a commonly used radionuclide like technetium-99 or cobalt-57. Energy windows may be adjusted manually or automatically by the camera. Energy window widths of 15% or 20% are commonly used. If the window is too narrow, some of the photopeak photons are lost, and if the window is too wide, scatter photons are included in the measurement. Uniformity is performed daily and after each repair. Uniformity can be done intrinsically with a point source of technetium-99 with the collimator removed. The point source is placed at about 5 times the diameter of the useful field of view of the camera. Uniformity images are acquired with 5 to 15 million counts and analyzed visually or with a computer program. This image shows an area where the photomultiplier was decoupled so that no data was collected. Extrinsic uniformity is done with a flat source of cobalt-57 or a fillable flat source. This is done with the collimator in place. Spatial resolution can be done intrinsically with a point source and a 4-quadrant bar phantom, or extrinsically with a flat source, the 4-quadrant bar phantom, and the collimator in place. The image shows a flat source, the red sheet, and a 4-quadrant bar phantom, the blue sheet. The grayscale is the acquired bar phantom image. Spatial linearity can be evaluated at the same time with the 4-quadrant bar phantom or with a separate linearity phantom. The sensitivity or efficiency of a scintillation camera is a fraction of X-rays or gamma rays emitted by a source that produces counts in the image. The system efficiency of a scintillation camera depends on the product of the collimator efficiency, the intrinsic efficiency of the crystal, and the fraction of counts accepted by the energy discrimination circuit. Sensitivity can be done intrinsically by measuring the counts produced by a point source of technetium-99 placed at different distances from the gamma camera head. Crystal efficiencies are better at different energies for thicker crystals than for thinner crystals, and this is shown on this bottom image. The performance of a gamma camera can be evaluated by measuring the uniformity, spatial resolution, energy resolution, and count sensitivity. The uniformity can be evaluated using software and compared to manufacturer's stated uniformity. The data should be recorded and compared to other uniformity measurements done over time. Spatial resolution is the ability of the camera to distinguish objects with different activities. Intrinsic spatial resolution can be evaluated using a line source filled with technetium-99 and acquiring an image of the line source. The image is analyzed by measuring the full width at half maximum of the line spread function. The resolution can be compared to the manufacturer's stated resolution. The data should be recorded and compared to other resolution measurements done over time. Energy resolution is the ability of the detector to differentiate between photons of different energies. It is determined by measuring the width of the resulting pulse height spectrum and using the formula shown. The pulse height spectrum of cesium-137 is shown with the 662 keV photo peak shown on the graph. The full width at half max is the width of the photo peak at half maximum counts. This is used in this formula to calculate the energy resolution of the detector. To obtain high-quality images in nuclear medicine, imaging procedures should be optimized for each type of study. The number of counts obtained should be sufficient to reduce the effect of quantum mottle on image quality. Count density can be improved by using count times optimized to be long enough for acquiring counts but also paying attention to patient motion. Contrast can be improved by using a narrow energy window to reduce scatter. Also, the choice of collimator can improve image quality. A high-resolution collimator can be used to improve spatial resolution, and properly matching low-energy radionuclides to low-energy collimators also improves image quality. Another type of image acquisition in nuclear medicine involves emission tomography. Emission tomography involves the emission of gamma rays from an organ and the detection of the gamma rays by a scintillation camera detector. The camera rotates about the patient and acquires projection data. The patient or object remains stationary during the acquisition, and the camera rotates about the center of rotation. The images acquired are reconstructed by using a filtered back projection algorithm or iterative reconstruction. We shall learn more about this when we learn about SPECT in the next lecture. There are some artifacts that can degrade the image in emission tomography. These are based on attenuation, scattered radiation, spatial resolution, noise, uniformity, and motion. Attenuation artifacts arise because the gamma rays emitted in the body have to travel through tissues of different thicknesses and densities before emerging from the body. Those gamma rays coming from deeper layers are attenuated more than those coming from shallower layers. Also, lower energy photons are attenuated more than higher energy photons. This causes the camera electronics to map deeper layers as low intensity in an image. There are methods for attenuation correction that we shall learn about in the next lecture on SPECT and PET. Scattered radiation from both the patient and collimator can degrade image quality in an emission tomograph. Scattered radiation from material around the source can be captured by the detector if the energy window is set too wide, allowing the detection system to include Compton scattered photons in the photo peak window. The figure shows a spectrum in air and in the neck, showing there are more scattered photons in the neck. This may be corrected by setting a narrower energy window that excludes scattered photons in the spectrum, as well as pulse height discrimination by the electronics of the camera. We shall learn more about scatter correction when we learn about SPECT in the next lecture. Statistical noise is present in all radioisotope imaging and is a particular problem in emission tomography because the ramp filter used in filtered back projection reconstruction also automatically amplifies the high frequency noise present. When smoothing filters are used to reduce noise, they lead to a degradation of the spatial resolution. Different types of filters are available for pre- and post-reconstruction filtering, as well as choices for smoothing. The images shown on this slide are for various common filters like the ramp Hanning and Shep-Logan filters. We shall learn more about them later. Non-uniformity issues that degrade image quality in emission tomography can be traced to either the detector or collimator. These non-uniformities will show up as circular artifacts in the image unless corrected. The correction for non-uniformities is to acquire a high count flood of 30 million counts. We shall learn more about non-uniformity correction in the next lecture. Motion artifacts in emission tomography arise because of patient or organ motion. Patient or organ motion can be registered because of the long acquisition times used in imaging. Acquisition times can go from 20 to 30 minutes or longer depending on the study. There are methods to correct for body motion and for organ motion that involve using fiducial markers for body motion or positioning for organ motion. We shall learn more on this in the SPECT lecture. Let's finish up with a few questions. First question, the most commonly used collimator in planar imaging is, and your choices are pinhole, parallel hole, converging, diverging. The correct choice is parallel hole collimator. Second question, which of these quality control procedures is done to center the energy discrimination window on the photo peak of the radionuclide energy? The choices are uniformity, spatial resolution and linearity, efficiency, peaking. The correct choice is peaking. This is the last slide. Thank you for watching this presentation.